Hello, this is Ahmet Ozer. I'm a professor at Western Kentucky University.
I'm Ahmet Kaan Aydin, a PhD student from UMBC.
We appreciate the support of NSF to make this research happen. This talk is centered around how to come up with a filtering algorithm for sensor data for the finite difference-based model reduction of a piezoelectric multi-layer beam. Right, here's the multi-layer structure with arbitrary number of layers. We have M+1 elastic piezoelectric combo of outer layers, and then these constrain M viscoelastic layers. And if you consider the three-layer beam model, simply we have elastic, viscoelastic, and piezoelectric combination. And we have some modeling assumptions. We have no independent longitudinal vibrational dynamics across the layers. We have only uniform bending across the layers, so all layers are going to bend uniformly. And the layers are perfectly bonded and no slip occurs. And the outer layers resist transverse shear, but the middle layer, since it's more like a viscoelastic type material, it's going to allow transverse shear, and that generally creates a passive damping in the structure, and the resulting PD model is a linear.
The main objective of our research is to design a robust sensor that can be used to construct an accurate actuator that controls the vibrations on the beam. The gauge on the right shows the feedback controller, which is the angular velocity at the tip of the beam. The gauge on the left is the total energy of the system, which is normalized with respect to initial energy. So let's run this simulation here. From the literature, we know that a blind application of the model reduction causes some problems. And in our simulation as well, we see that the decay on the total energy is very slow. And not just that, the beam still has some high frequency vibration. We will present today the reason of this discrepancy and how it can be fixed as well.
Here's the PD model for the three-layer case. We have dots and primes denoting time and space derivatives. We have two dependent variables. One is the uniform bending of the center line of each layer of the three-layer beam, and then the phi representing the transverse shear angle of the viscoelastic layer. And these are coupled through this PD system. And we have hinge boundary conditions, and all of the material constants are hidden into the constants B, C, and P, and these are all positive. From the three-layer beam model, you may consider what changes when you jump into the multi-layer beam model. We still have the uniform bending of the center line of the laminate. And this time we have a shear for each viscoelastic layer, so we will have a vector representing that, and the second equation turns into simply a vector equation. And all of the constants BCP now turn into matrices, and out of which P and C are invertible, symmetric, and positive definite matrices.
In our presentation, we will go over the three-layer case proofs. However, you can see the proofs for the multi-layer case in our paper. Observe that second equation in our PDE is an elliptic one, so we can solve the shear angles phi in terms of the bending z. When we solve the shear in terms of the bending and substitute it back into the first equation, we get a more compact version of our PDE here. In this case, we observe that this is very similar to the earlier Bernoulli beam model that represents the single-layer case.
Here's the natural energy for the three-layer beam model. During the motion, kinetic, bending potential, and shear potential energies are exchanged. If you're familiar with proving observability for earlier Bernoulli type beams with hinge boundary conditions, we generally go with a lower order energy, as you see here. And since we don't have any controller and we're just designing a sensor, so the system is simply conservative.
Our main goal is to prove exact observability of the system. Exact observability is the ability to find any unknown initial data by the observations made over a finite time. Exact observability is a dual problem of the exact controllability, so proving one implies the other one. Exact controllability has been proven before for the three-layer case. However, this proof does not state the sensor measurement explicitly. It is not generalized to the arbitrary number of the layers either, and it does not consider the model reductions to the finite dimensions. All of these are the goals of our research as well. How can we prove the exact observability? It is equivalent to proving exact observability inequality, as you can see here, where the z prime term here is the deflection angle of the tip of the beam and our sensor measurement. If we can prove that the energy is bounded by these observations, then the system is exactly observable. This inequality implies if I have made no observations over time, so if this side is 0, then the energy of the system must be 0 as well, so the system is in the resting position. On the other hand, if there is any energy on the system, then I must make some observations over the time.
Now the question turns out to be how to prove uniform observability, which will lead to the sensor design in the finite dimensional setting. If you're familiar with Euler-Bernoulli type beam models, we have two widely used methods. One is the multipliers method, and the other one is more like spectral approach and using a non-harmonic Fourier series. And for the chosen set of boundary conditions, spectral analysis is the best because we can accurately describe the spectrum, and we can prove that for arbitrarily small time, this exact observability result works true with only one measurement. And here the proof is based of the deflection, comparing the eigenvalues of the Euler-Bernoulli beam model to the eigenvalues of the Meade-Marcus beam model. We have the blue dots representing the first 30 eigenvalues of the Meade-Marcus beam, and the red ones are for the Euler-Bernoulli beam. And we can simply observe that blue ones are always on top of the red ones. And as well, for the uniform gap among the eigenvalues, the blue guys are always on the top of the red guys. Having a uniform gap is super important in proving exact observability result, because if the eigenvalues get extremely close to each other, the sensor gets numb to distinguish one mode from another. So the whole proof in the paper is based on this idea.
As I mentioned before, we know the eigenpairs of the system explicitly. By using these eigenpairs, we can represent the solution of the system as well. And if we substitute this solution into the energy, we get a good estimation in terms of the eigenvalues and the Fourier coefficients. And for the boundary sensor measurement, we use a theorem known as the Horner's theorem with the uniform gap result. And by using this, we can find the similar estimation for the sensor measurement as well in terms of the eigenvalues and the Fourier coefficients. So since we have the same estimation for both terms, this implies exact observability inequality.
All right, since we're done with the PD model, now we can change the gear to the finite difference model reduction, and we simply discretize only the space variable x, so the length of the beam is split into n equal pieces, and because of the higher order derivatives in the model, we have fictitious nodes z-1 and z-2, and now the laser sensor observes the angle of the deflections at the tip of the beam based on z sub n, because z sub n plus 1 is simply 0 because of the hinge boundary condition, so we only observe z sub n. Our model reduction is based on how we approximate the second order space derivative by central differences. In fact, this corresponds to this nice tridiagonal band matrix, and for this matrix we know the eigenvalues explicitly for any dimension, and we're going to try to utilize this matrix towards understanding our reduced model. All right, so since we have AH, we can write down the reduced model in terms of AH only. And as you follow from the slide, J is the inverse of CAH plus PI, which is in fact a positive definite matrix. And the lower order energy is also discretized. And in fact, we spent a lot of time to come up with a nice discretization, so we can still preserve the conservativeness of the PD model into the reduced model. So one thing that we can observe from our model is that it's a good perturbation of the early Bernoulli beam model, and what has been done about the early Bernoulli beam model in terms of uniform observability. So since everything is based on this AH matrix in constructing the reduced model, so some properties of AH can tell us what's going on in reality. So essentially, as H goes to 0, the eigenvalues of AH, well, especially for high frequency ones, get extremely close to each other. So that makes AH matrix lose its observability property because the uniform gap is lost as H goes to 0. And one of the remedies proposed in the literature is the direct Fourier filtering model. And we should probably appreciate two works here in Fontaine-Zouzoua and Leon and Zouzoua, one for wave equation and the other one is early Bernoulli beam model. And we recently did a similar type of approach for the Rayleigh beam equation with hinge boundary conditions. And recently, there are more works on the piezoelectric beam equations and the wave equation with stabilizing feedback controllers.
We'll pass over this part. Here we have the explicit representation of the eigenpairs of the reduced model. It's important to note that here, lambda k and the phi k are the eigenpairs of the matrix AH, which was the reason of the lack of uniform observability in the early Bernoulli case. And when we try to prove the uniform observability, we face the same problem here as well. In this equality here, the left-hand side is the highest frequency eigensolution corresponding to the energy. And in the right-hand side, we have the highest frequency eigensolution corresponding to the sensor measurement. And if you look at this denominator here, we see that this denominator goes to 0 as h goes to 0. So the whole term here blows up, which implies it is impossible to bound energy by the sensor measurement we have. So the system lacks uniform observability as h goes to 0. So let's look at what we have done so far. We have proven that PD model is exactly observable, and we reduced the PD model to the finite dimensions by using a very well-known and well-tested method of the finite differences. And what we end up having is the reduced model is not uniformly observable. So we have a problem here, and we need to see what this problem. When we look at the gap among the eigenvalues of the PD model and the reduced model, we see that for the reduced model, the gap decreases as we go to the higher frequency eigenvalues. This implies that sensor is unable to distinguish these high frequency eigenvalues from each other. Moreover, these high frequency eigenvalues are diverging from the corresponding the eigenvalues of the PD model. How can we fix this problem? An easy and direct approach is to apply direct Fourier filtering. We choose a filtering parameter gamma here and consider only the eigenvalues that holds this filtering condition in our solution. And if you want to keep more eigenvalues, you can just have a larger discretization of the system. Let's say you want to keep 100 eigenvalues. You can just discretize for 150 and keep 100 of them.
One of the aspects of our research is to demonstrate our findings in real-world applications, and Wolfram allows us to do that. And Wolfram demonstration project site has already more than 12,000 interactive demonstrations, and we have already published several of them.
Here you see a snapshot from one of our published projects for the cantilevered beam. As you can see, user can choose the physical parameters of the system very freely. Moreover, these demonstrations are done different choices of the initial conditions, methods, and the layers as well. At the start of the presentation, we have shown you this simulation of the 7-layered beam. As you will remember, the total energy of the system was decaying very slowly. Now we know that the reason for this is the spurious high-frequency eigenvalues. And you see that no matter how much we wait, we have these high-frequency vibrations on the beam as well. So let's apply some direct filtering and see what happens. After the direct filtering, we see that the vibrations on the system dies down almost immediately, and the system goes to the resting position. The energy of the system decays to zero, and the feedback controller will go to the zero over time as well. And this is a more realistic representation of the actual beam itself. So let's look at the eigenvalues of the closed-loop control system. We see that these high-frequency eigenvalues are accumulating towards the imaginary axis. As you know, the decay rate depends on the real part of the eigenvalues. So here we have a very slow decay rate of 0.11 because of these high-frequency eigenvalues. Moreover, these are farther away from the corresponding to eigenvalues of the PDE model as well. After filtering these high-frequency eigenvalues, we see that the remaining eigenvalues are farther away from the imaginary axis. So the decay rate for the remaining eigenvalues is 3.58, which is much faster than what we had before filtering.
All right, here's the ongoing and future work. We worked also on the model with the same model with cantilevered boundary conditions, but we used a different approximation strategy that detours the whole filtering. And we did the same thing for hinge boundary conditions, like the same one that is worked out in the CDC paper, but that's an ongoing work. And for the model that we considered here, we are working currently on designing a stabilizing controller, but the mathematical proofs are a little bit more complicated when you try to prove exponential stability. And we have a lot of Wolfram demonstration projects going on with my undergraduate research team. They have one already published and another one on the peer revision. And just for those interested audience, and Wolfram peer revision takes long sometimes. Just be patient with them before they put anything published in their website. And the generalization to arbitrary number of odd layers, in fact, this is the demonstration that you see, but that's not in their final form. That's not in the publication form yet. We're still working on polishing that up. And here are some references for interested audience. All right, thanks for listening. Bye.